So what are the operations we can do with these linear vector functions that we're describing with matrices? So if we have two systems of linear equations like this, right, each of them we can represent each left-hand side using a matrix. So for the one on the left, this linear vector function would be a11x1 up through a1nxn down to am1x1 plus up to amnxn, right? And we would represent this with the matrix a11 to a1n down to am1 up to amn. And we could do the same thing for this other system. This would give us the matrix C11 up through C1n down to Cm1 over to Cmn. And notice that these are both m by n matrices, right? Well, one thing you could do with these, I guess I didn't write down the linear vector function for the second one. One thing you can do with these two linear vector functions is, well, since they're both producing vectors, you can add these linear vector functions, right? How do you add vectors? Well, you just add them component by component. Right? So add first components, add second components, all the way up to last components. This produces a linear vector function that looks like, well, the first row is just the sum of these first two rows. But there are two terms with an x1, we can factor that out. So that's a11 plus c11 times x1 plus, and so on, up to a1n plus c1n times xn down to am1 plus cm1 times x1 plus dot 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 plus amn plus cmn times xn. Okay, and what is the matrix that represents this linear vector function? Well, again, the matrix that represents a linear vector function is just the matrix of coefficients. So that's going to be a11 plus c11 over to a1n plus c1n down to am1 plus cm1 over to amn plus cmn. So when we add two matrices, what we get is another matrix of the same size, and we just add each entry. We just add the entries term by term. Right? So add corresponding entries to get your sum matrix. Now, if I asked you to guess the definition of how you should add matrices, this is probably what you would come up with. But the important idea here is we are coming up with this definition of matrix addition by thinking about how you operate on the corresponding linear vector function. So since, for sums, that gives you about what you would expect, so that might not seem so important, but it will be important later, trust me. So let's look at an example of adding matrices. So let's add these two matrices. Notice they are the same size. If your matrices aren't the same size, then it doesn't even make sense to add them. But these are the same size, so what do you get? So this is a very unexciting arithmetic problem. Rather than when you add two numbers, you just add the two numbers. When you add two matrices, you have a bunch of different additions to do, one for every position in the matrix. So in our 1, 1 position, 2 plus 1, that's 3. and then 1 plus 0 is 1, and 0 plus 1 is 1, minus 3 plus 4 is 1, 2 plus 4 is 6, 1 plus negative 5 is negative 4, 4 plus 6 is 10, 5 plus negative 2 is 3, and negative 2 plus 3 is 1. Okay, so you can see adding matrices, there's not anything difficult going on here. You really do just add them term by term. But one thing that's important to know about addition of matrices is what are the algebraic properties of this matrix addition. In every other situation where we have an addition, that addition behaves nicely. And when I say nicely, what I mean is things like associativity of that addition, commutativity of the addition, that sort of thing. So does our matrix addition have these same properties? So for example, associativity of addition. Remember, associativity of addition is the idea that if you have two different additions like this, A plus B plus C, if you do them in the other order, A plus B plus C, that these should actually be the same. Should be the same if the addition is associative. This is definitely true for real numbers. It's definitely true for vectors. Is it true for matrices? Well, we can check if it's true just by actually writing out these additions. So, of course, all of these matrices have to be the same size. So A is the matrix Aij. Remember, this is just an abbreviation for all of the entries in this matrix. B is the matrix little bij. And C is, oops, we need a plus here. C is the matrix little cij. And we want to check, is this equal to, if we do the addition the other way, so that's little a sub ij plus, and then in parentheses, little bij plus little cij. And on the left here, if we actually do this addition, we would have to do it in two steps. I guess the first step would be first add this stuff in parentheses. That would give you a matrix that looks like, since we add matrices entry by entry, when you add the A's and the B's, you get Aij plus Bij, like this. And then afterwards, the plus Cij. And what that gives you at the end is a matrix whose entries are Aij plus Bij plus Cij, which is, of course, exactly what you would expect. When you do everything with adding the B and C matrix first, of course, you get the same thing, right? What this all comes down to is, since matrix addition just happens entry by entry, well, adding entries is just regular old real addition, and real addition is associative, and so matrix addition will also be associative. All right, what about other properties of multiplication, like, for example, commutativity? Commutativity is the idea that if you are adding two things, you can turn that addition around and you still end up with the same thing. So we get equality here. Of course, this is just as true for matrices as it is for anything else, because the sum on the left, A plus B, if you write it out in terms of entries, that's Aij plus Bij. The sum on the right, in terms of entries, is little bij plus little aij, but real addition is commutative, and so these things are really equal. There are a couple other less obvious properties of addition that actually turn out to be pretty important for doing algebra. One is the existence of an identity for addition. An identity means just something that if we take some matrix, if we add our identity, we get the same matrix back. So any matrix you can put into this slot is called an identity for this operation. So this is an identity for the matrix sum. And if we were talking about real numbers instead of matrices, you would probably recognize that what we're looking for here is just 0. Well, what is 0 when we're talking about matrices? It's the 0 matrix of that size. So you might guess, well, maybe the identity for matrix addition is just the 0 matrix of the appropriate size. And of course you'd be right, because if you take the matrix A, which is just all of its entries are little a ij, and you add a matrix of the same size that's nothing but zeros, then when you do this addition entry by entry, you get, right, each entry is a sub ij plus 0, and of course 0 is, this 0 here is not the matrix 0, it's just the number 0, the scalar 0, and that's the identity for scalar addition, so this is just a sub ij. So there is an identity of every matrix size, it's just the 0. Another important algebraic property for addition is that there are always inverses for addition, right? So by inverse, what we mean is something that if you start with a number, an inverse for this operation, so here I'm using scalar addition for an example, an inverse is something that when you add it to your original, you get the identity. And remember, for real addition, the identity for addition is 0. So an inverse is just something that when you do the operation gives you 0. For real addition, you can see that what we're talking about here is just a negative. So for real addition, there's always an additive inverse. What about for matrix addition? Is there always an additive inverse? If we have a matrix aij, is there some matrix that we can add to it to get the additive identity here? And remember, the additive identity is the 0 matrix of the appropriate size. And of course, there is. It's just the same matrix but with negatives in every entry instead of, right, you just switch the sign on every entry. So for matrix addition, there is always an additive inverse. It's just the negative of the matrix that you started with.